In this video, we're going to take a look at the principle of inclusion-exclusion. So in finding the union of sets, which is what the principle of inclusion and exclusion does for us, we want to first take a look at a question where there's no overlap of sets, or the sets are disjoint. So in the real estate ads, there are 100 homes for sale with garages and 42 with swimming pools, but there are no homes that have both a garage and a swimming pool. How many total homes are for sale? Well, this is very straightforward. If there's 100 with a garage and there's 42 with a swimming pool and there's no overlap, that's a total of 142 homes. However, now let's say there's still 100 homes with garages and 42 with swimming pools, but there are 29 that have both a garage and a swimming pool. So how am I going to go about finding this? Well, there's different ways to think about it. I can find how many have a garage but no swimming pool, and that would be 71. And how many have a swimming pool but no garage, and that would be 13. And then how many have both, which is 29. So I could do it this way, and in doing it this way, I would take 71 plus 13 plus 29. And how many total homes would be for sale? Well, not 142 anymore. Now we would end up with 113. Now, it doesn't make sense for us to have to do it that way every time, especially if you have, say, 3 sets or 4 sets or 5 sets. So what we want to do is start to generalize a formula that we can use. So we're going to start by taking a look at the principle of inclusion-exclusion for 2 sets, which quite often in textbooks will be called the general rule of addition. And when we're doing this, essentially what we're saying is if you want to find the sum of 2 sets, the sum of the cardinality or the union. So remember these, if I didn't make that clear before, when you have these what look like absolute value brackets, we're talking about the cardinality or the number of elements in a set. So we're saying the number of elements in the union of 2 finite sets can be modeled by taking the number in A, the number in B, and adding those together, but then subtracting the overlap. And so here's how that works. Let's look back at our example that we just looked at. We said there were 100 homes for sale with garages. So we're going to call that A. I should probably make that green since that's what I used up here. So that means everything inside here must add up to 100. 42 with swimming pools, and I used orange for that. I don't have orange. Nice. We'll call this red. So this is 42, but again, everything inside of here needs to be 42, a sum of 42. So now if I plug in that 29, that's where that minus 29 here is going to come into play. So 100 minus 29 is 71. So 71 total, and then 42 minus 29, remember, was 13, so 13 total. So again, this is just a way for us to not have to do that math. So if I have to draw out the Venn diagram, again, not super friendly, but this formula says take 100 plus 42 and subtract the 29 just one time. So again, that's still going to give us that same result, which was 113 that we found before. But let's talk about why this works. If I am adding, I'm going to erase these numbers. I'm adding all of A, and then I'm adding all of B, but then I'm subtracting this one time. Notice that all it's going to do is subtract the 29 one time. So really, I'm either going to subtract it from A or I'm going to subtract it from B. We only have to subtract it once because by what I did here is I added it once, I added it twice, so I have to undo that second addition of the 29 by subtracting it. Let's look at a couple of practice. The first one, you will see quite often questions like this. How many positive integers not exceeding 1,000 are divisible by 7 or 11? So obviously the details could change, but it's the same idea. Now, what's important to understand here is that 7 and 11 are not only prime, but they're relatively prime, meaning they don't share any common factors. And that's going to be important if you're going to use the method that I'm going to show you. So obviously I don't want to list all of the numbers from 1 to 1,000. So instead what I can do is I can say let A be the set divisible by 7 and B divisible by 11. And if I take 1,000 divided by 7 and then I do the floor function is going to give me whatever the value is rounded to the lowest integer. So what I really get is 142.8 something, I believe. But I don't care, I only need the 142. So that's what this floor function does, as opposed to the ceiling function, which I believe we've talked about before, which you would round up to the next value. For B, I'm going to follow that same strategy, 1,000 divided by 11, and that gives me 90. And then of course, our principle of inclusion-exclusion says A union B would be A plus B minus the intersection. And so now I have to determine the intersection. So I've just determined 142 and 90, and I have to determine what is A intersect B, or in context, what values did I count as both divisible by 7 and 11. And so that's where it's very important that these two are relatively prime. So 7 and 11 is 77, and that gives me 12. So then you just use your calculator, add and subtract, and you end up with 220. Same idea down here, but a little less math involved. I'm going to use the same function. Instead of writing it out again, I'm just going to start adding. So I've got 53 computer science majors, 28 math majors, and 17 who are double majors, which means they were counted here and here. So how many total are enrolled in discrete math, or in other words, what is the union of those two sets? And that is 64. Now let's take a look at the principle of inclusion-exclusion for 3 sets. So for 3 sets, again, I'm going to add everything in A, and notice quickly that A is this circle, but there's all of these parts. So I'm just going to put one marking so we know that I've added each of those once. And then for B, that's everything in this circle. So I'm going to have to use green for B because I don't have an orange color. So I'm going to add one here, one here, one here, one here. And then everything in the yellow circle. So one here, one here, one here, one here. Now we can see what the problem is right now. I can see that the problem is that I've added this section twice, this section 3 times, this section twice, and this section twice. So if you'll notice on my next step, I'm now going to subtract A intersect B. This is B, this is C. So I'm subtracting this guy and this guy because that is where these two overlap. And then I'm going to subtract A intersect C. So that's this segment right here. So I'm taking 1 away from each of those. And then B intersect C. So that's this section from here and from here. And now again, you can see exactly what the problem is while I've subtracted each of those sections, this middle segment is now missing, and that middle segment represents anything that would be in all 3 sets. So that is why I have to add it back in. So by adding it back in, I now have accounted for all of the regions of my Venn diagram. So let's apply what we just learned about 3 sets And again, we're just going to use the same strategy that we used before. But if you'll notice, this question includes 3. Before it was 3, 7, and 11. So I'm going to call this set A and this set B, which is 1,000 divided by 7. And then this is set C, which is 1,000 divided by 11. And again, I'm just going to use the floor function for these just as I did before, because we want how many that are not exceeding 1,000. If we use the ceiling function, it would include the next digit above 1,000 that was divisible by that value. So these are the same values we found before. Obviously, I've included 333, which was not found before. Now I need to find the intersection. So again, I'm looking at A, union B, union C, and I'm going to add A and B and C, and I'm going to subtract A intersect B, subtract A intersect C, subtract B intersect C, and then I'm going to add the intersection of all 3. So A intersect B, just as we did before, would be divisible by the product of 3 and 7, or 21. And that gives me 47. And then A intersect C would be divisible by the product of 3 and 11, or 33. That value gives me 30. And A, whoops, wrong bracket, B intersect C, which is 7 times 11, or 77. And that gives me 12. So then I'm going to find this last value, A intersect B intersect C, which is A intersect B intersect C, which is anything divisible by the product of all 3. So 3 times 7 times 11, which is 231. And that gives me 4. So my final solution is add 333 and 142 and 90, subtract 47, 30, and 12, and add 4. And that gives me a result of 480. For this second question, I wanted to throw in a little bit of a kink. And the reason that I did that is because it gets very tedious, I think, to do the same kind of question over and over and over. So what we're going to do this time is, if you'll notice, that very, very first phrase says there's a total of 1,109 students that take foreign language, which means as I'm working through, and I'm just going to recopy this, as I'm working through this, instead of trying to find the union, they've essentially given me the union, and they're going to ask me to find something else. So let's start filling in the blanks and seeing what they're asking me to find. So this tells me 1,109 students total. And we're going to call Spanish 796, or Spanish A, so 796 in Spanish. B will be French, so 285, and 97 in Chinese, so that's going to be C. A intersect B would be Spanish and French, and that is 42. A intersect C would be Spanish and Chinese, which is 17. And B intersect C, French and Chinese, which is 15. So the only thing they don't tell me is who has taken all 3. And if you'll notice, thank God, it says how many have taken a course in all 3. So that is the question, is how many have taken a course in all 3. So really this is just a matter of getting your calculator out and adding these together. So I get 1,109 is equal to 1,102 plus the intersection, A intersect B intersect C, and that gives me 7 is in A intersect B intersect C. So the answer to the question is 7 students have taken a course in all 3. So as I'm sure you've probably guessed, there is a principle of inclusion-exclusion for n number of sets, and it should not come as a surprise to you. What we're going to do is exactly what we've done to this point. We're going to add all of the cardinalities of single sets. We're going to subtract the cardinalities of the intersection of 2 sets, add the cardinalities of the intersection of 3 sets, subtract for 4 sets, add for 5 sets, so on and so forth and so on and so forth. So this really gives us a good idea of exactly what's happening. This -1 is oscillating. It's going back and forth between addition, subtraction, and then the intersection through however many values we have. Here's your last practice, and instead of giving you a question where you had to find the union of 4 or 5 sets, I decided to just give you a practice where you were finding the union of 3 sets, but you had to do a little bit more mathematical work to find it. So press pause, try this question, then press play to see how you did. So again, we're looking at permutations of the 10 digits, that's digits 0 through 9, there are 10 of them, that either begin with 987, contain 4, 5 in the 5th and 6th positions, or end with 1, 2, 3. So we're going to call 987, that's going to be my first set, and then 4, 5 is going to be my second set, and 1, 2, 3 is going to be my third set. So as I'm working through this, I'm going to remember that there are 6, 7, 8, 9, 10 spaces. So it says permutations, which means we're permutating all 10 digits. And for the first one, I'm starting with 987. So there's a 9 here, an 8 here, a 7 here. Now there are 7 spaces left, and there are 7 digits left, which means that's 7 factorial. For 4, 5, in the 5th and 6th positions, so 5th and 6th positions, again, there are 2 spaces that are basically reserved, and the rest, or 8 factorial, are left to permutate all of the other digits that I haven't yet used. Same thing for 1, 2, 3. It ends in 1, 2, 3, which means there are 7 left and 7 digits. So that would be my sets A, B, and C. So now I want to look at the intersection of these 2 sets, which means it starts with 987. I've got 4, 5 in the 5th and 6th positions, which means there's 1, 2, 3, 4, 5 spaces left to permutate the 5. I'm going to find the intersection of 4, 5 and 1, 2, 3. So there's 4, 5 and 1, 2, 3, which means 5 positions are taken, which means there's 5 left over to permutate. And then I'm going to find, oops, that was supposed to be a 3, sorry about that. Then I'm going to find the intersection of these 2 sets, which means starts with 9, 8, 7, and ends in 1, 2, 3, which means there's 1, 2, 3, 4 spaces left. And then finally, I need to find what happens when I find the intersection of all 3. So this is A intersect B intersect C, which is if I have 987 and then I have 4, 5 here, and then I have 1, 2, 3, which means there's just 2 left and 2 digits, so 2 factorial. So A intersect B, A union B union C will be found by taking A, which is 7 factorial, plus B, which is 8 factorial, plus C, which is 7 factorial. Then I'm going to subtract A intersect B, 5 factorial, B intersect C, which is 5 factorial, and A intersect C, which is 4 factorial, and then I'm going to add back in 2 factorial. And I would go ahead in this case and find the exact solution, which is 50,138. Well, we did do some practice here for the principle of inclusion-exclusion. The next video is all applications of the principle.